How do you replace a technology that has been battle-tested for literally over 100 years? 1968 saw a new type of transformer enhanced with power semiconductors, the solid-state transformer, or SST. The SST is significantly smaller and adds some special functionality to your regular transformer. But despite being almost ready, quote-unquote, for 50 years, hype cycle after hype cycle has passed without much success. Can AI data centers finally be that killer app? In this video, we profile the solid-state transformer. This video is brought to you by the Asianometry Patreon. Transformers transform voltage and current from one level to another. Modern transformers operate on the same physics as the original device shown off by the sexy Michael Faraday when he first demonstrated induction over 100 years ago. It is made from two coils of copper wires wound around a shared iron core. If you pass an alternating current through the first of two copper coils, its changing magnetic field will induce voltage in that second copper coil. But while the transformer's core operating principle has not changed, the thing's designs have diversified, kind of like how the internal combustion engines of a Ford Model T and a Lambo use the same principles but look radically different today. You can find all sorts of different transformers in the modern power grid. Most are hidden inside unassuming but ubiquitous containers that people don't look at twice. There's a transformer mounted on your telephone pole. It's a gray cylinder thing, or one on the street, maybe with a nice paint job. And there are many smaller transformers scattered in your home, inside your phone charger, for instance, or your microwave oven. The transformer is the anonymous lunch pail worker of the grid. So despite all the world's technological progress, the transformer has not changed all that much, and for good reason. They're simple, 98 to 98% efficient, and have a history of good reliability. But for all of its upsides, the transformer has limitations. Most noticeably, the traditional transformer is large and bulky. There's an inverse relationship between a current's frequency and the size of its transformer. Since the power grid runs at a relatively low frequency of either 50 or 60 Hz, that means that the transformer has to be physically large. Another major issue is that the transformer is fundamentally passive. It cannot perform fast electronic regulation or clean up waveform defects without additional equipment. So any problems in the waveform, like voltage dips or spikes, simply pass through. Fair enough, but the emergence of power semiconductors like the thyristor in the 1960s brought forth new possibilities. Why not combine transistors and transformers to get something new? In 1968, a research engineer at General Electric named William McMurray filed a US patent that combined solid-state power semiconductors with a high-frequency transformer. It takes in a low-frequency current and then uses power semiconductors to chop up that current to raise its frequency to maybe 5,000 or even several tens of thousands of hertz. Now that the current is of a higher frequency, we can use a physically smaller transformer to step the voltage up or down. After that, another set of power semiconductors can lower the frequency back down to 50, 60, or whatever hertz for actual use. This is the core concept behind the solid-state transformer. Power electronics coupled with high-frequency transformers to shrink the whole device's footprint by a significant percentage, in some cases 70 to 80%, while also providing some form of controllability. I was not able to dig up whether McMurray and GE ever built a commercial version of the thing he patented, which he called at the time the electronic transformer, though a few sources did say he built a prototype. The patent also does not explain where the idea came from, but I wonder if it has to do with GE's work with European trains. Electric trains in the German-speaking countries in Scandinavia, so Germany, Austria, Switzerland, Norway, and Sweden, run at a standard frequency of 16.67 Hz, so that is even lower than the 50 or 60 Hz in the world power grid. The reasons for such a low frequency are historical and to me kind of amusing, but the consequences are literally large. Since a transformer's size is inversely proportional to the power frequency, a 16.67 Hz transformer ends up being substantially larger than a 50 Hz one, which is not ideal in a constrained environment like a train. More on this later. There were a few reasons why the US Navy started studying solid-state transformers in the 1970s. One reason had to do with the transformer's passive nature. It lets waveform defects pass right on through, which can pose a problem for sensitive military systems like radars. Their existing transformers use a PCB-based chemical called ascarel for cooling and electrical insulation. Unfortunately, ascarel is toxic and accumulates in nature, causing health problems. But since removing it is so difficult, they were looking for an alternative system. Another practical reason involved power savings. This is during the energy crises of the 1970s, and efficiency was the word of the day. When ships berth at port, they take power from the shore, but their power loads were variable and unpredictable depending on task and ship type. While a traditional transformer's nameplate efficiency can reach 98%, that efficiency varies with loading. When loads are variable, you get losses, and the Navy estimated that tens of millions of dollars are lost to distribution inefficiencies, which wasn't ideal. After seeing how certain sequences of power semiconductors can replicate voltage step-down behavior, the Navy hired a contractor to run computer simulations and do breadboard testing for a feasibility study. That study concluded that a possible solid-state transformer can compensate for its lower overall efficiency with consistent performance under variable loads. I would note that few would consider what the Navy explored to be a true solid-state transformer today. There were circuits without a high-frequency transformer inside, meaning that it did not isolate parts of that circuit to prevent current flow. They call this galvanic isolation, and normal transformers have it. Anyway, so it is slightly ironic to me that this 1980 paper coined the name solid-state transformer, which of course stuck. The paper concludes that a tremendous amount of R&D and testing work laid ahead, but predicted that the solid-state transformer could become the, quote, building block, end quote, of electrical conservation schemes, and a practical one laid maybe 10 to 15 years away. While this prediction did not come to pass, occasional development efforts continued. In 1995, the American-based Electrical Power Research Institute, EPRI, sponsored some of their first research on SST prototypes. The work would slowly continue into the early 2000s, eventually producing what they called the Intelligent Universal Transformer. In 1996, a team in Japan led by Kosuke Harada of Kyushu University proposed the Intelligent Transformer, which is largely a newer version of McMurray's transformer but with more modern silicon-based IGBT power semiconductor switches. While it worked and offered benefits that traditional transformers cannot provide, like controllability and smaller size, its peak efficiency was about 80% overall. This was not enough to compete against traditional transformers, and in the 1990s, power semiconductors had not yet reached the performance levels needed to make the concept practical. In 2007, the Swedish-Swiss company, ABB, presented a prototype of what they called Power Electronic Traction Transformer, or PET. They had developed this solid-state transformer variant for trains. Yes, we are back to the world of trains again. ABB's work targeted one type of transformer inside the train, the traction transformer, which steps down voltage of the line power so to feed an electric train's traction motor. Unlike a standard transformer, the traction transformer must fit inside a constrained space beneath the train's floor. For that reason, as well as the fact that the car's abrupt stops and starts causes damaging shocks, designers optimized this traction transformer for size and resiliency rather than pure efficiency. So it tends to be more like 90% efficient than 98%. Despite that, it is still one of the heaviest bits on the train car, which adds energy consumption as well as wear and tear. So it seemed like a unique opportunity for the solid-state transformer. The PET that ABB presented was a 3-stage device. The first stage takes an AC input from the line and raises the frequency using silicon IGBTs, which stand for insulated gate bipolar transistors, and became commercially available in the 1980s. The second stage is a medium frequency transformer that steps down the voltage. Then finally, the third stage is a converter that can produce power that feeds into the train's traction drive. ABB continued to work on the PET until at least 2012, when they presented it at the InnoTrans 2012 show. This most advanced PET boasted unprecedented efficiencies of 95 to 96%. It was half the size of a regular transformer, making it far easier to stick under the floor. There were over 20 prototype PET-based systems introduced, including from big train makers like Alstom, Siemens, and Bombardier. However, the PET never reached the commercial stage despite delivering on various size/weight and efficiency promises. They were untested and seen as too complex and expensive, costing over 50% more than their traditional counterparts. Ultimately, interest moved away from railways to the power grid. One of the most significant obstacles in solid-state transformer progress was the insufficiency of silicon-based power semiconductors. Even the aforementioned 6.5 kilovolt silicon IGBTs start incurring significant losses when the frequency rises above the low kilohertz range. Or in the case of the PET trains, since the silicon IGBTs are rated only for 6.5 kilovolts, they cannot connect right to the 25 kilovolt power line, forcing additional system complexity and discouraging PET adoption. So the emergence of practical wide bandgap semiconductors like silicon carbide in the late 2000s caused a great deal of excitement. Though not yet cheap, they set off commercialization efforts to make solid-state transformers for a new, smarter energy grid. The idea was that as intermittent renewables replace fossil fuels, it gets challenging to store and control the flow of this energy. Distributed renewables like rooftop solar pose special challenges to the grid. Voltage swings due to passing clouds, voltage drops during peak demand times, voltage rises during low demand times, and other power quality issues. So we need new equipment. One popular concept from the Future Renewable Electric Energy Delivery and Management, FREEDOM, Center in NC State University promoted the idea of the Internet of Energy. In this vision, the solid-state transformer is more than just a tool to step the voltage up or down. The idea is by adding to the SST multiple interface AC-DC ports, we make it into the router of the energy internet, transforming electricity and distributing it to different subsystems. The solid-state transformer can handle the perceived problems of this intermittence. Researcher Alex Q. Huang, who is the main driver behind the whole energy internet idea, said, quote, "Solid-state transformers would make connecting a solar panel or electric car to the grid as simple as connecting a digital camera or printer to a computer. That would reduce our reliance on fossil fuels by making it easier for small-scale sources of cleaner energy to contribute to the grid," end quote. Excited by the possibilities, the smart transformer was chosen as one of MIT's breakthrough technologies of 2011, and a few startups emerged to build them. One was Varentech, which raised millions from prestigious investors like Bill Gates and Khosla Ventures. Initial news reports had them planning to build a solid-state transformer. Another was Amantis, which spun out from Cambridge University with intentions to build SST prototypes targeting wind farms. At the start, the solid-state transformer was seen as this massive market opportunity as utilities adopt renewables and build smart grids. One optimistic estimate in 2012 said that SSTs would grow 82% a year, reaching $5 billion by the year 2020. In the end, all of these SST startups pivoted away from SSTs. The product that Varentech eventually debuted were grid edge devices, electronics that accompany traditional transformers in delivering control of grid voltage while also providing grid analytics to utilities. Unfortunately, that market did not develop as hoped, and in 2021, the company's grid edge hardware and software assets were sold to Sentient Energy, a subsidiary of the Koch conglomerate. Another once-hyped grid electronic startup was Gridco, which raised $54 million but closed its doors in 2018. Many of these startups found that few utilities wanted to buy and roll out an energy router type SST. A recent episode of the Semi-Analysis Weekly podcast hosted Varentech's VP of Engineering and Ops from 2011 to 2013, Haroon Inam. Inam is now the co-founder and CEO of a startup called DG Matrix, and I will mention them later. Hold that thought. Inam recalled that the original idea at Varentech was to build an SST for AC to AC conversion with some power cleanup and value add. He reflected, quote, "We realized after 2 years of work and spending millions and millions of dollars that building an AC to AC solid-state transformer was probably one of the dumbest things we could have done. You're taking a hunk of iron and a hunk of copper that's going to last 40 to 50 years. Why the hell would anyone in their right mind try to replace that with a bunch of electronics that are going to be more delicate?" End quote. It also costs way more. Some estimates find that an SST might cost 5 times more than a traditional transformer, though that gap closes if we look at it on a system-level basis. Interestingly, Varentech's former CEO, Deepak Divan, went to academia afterwards, and he contributed to a 2022 paper finding that neither SSTs nor hybrid transformers, which merge transformers with a converter, to be economically viable without a 60% capital cost reduction. Anyway, the point is that SSTs will not succeed by doing what a traditional transformer can do. For it to be commercially compelling, it has to do something that transformers simply cannot do and that people are willing to pay for. Just being smaller or being able to handle voltage fluctuation is not enough. Time for us to talk about AI data centers again. Sorry guys. A major shift in these data centers has to do with their power usage. I'm not going to spend a lot of time explaining this. There are big semi-analysis articles you can read instead. But traditional data centers receive medium voltage AC power from the utility and run that through a hierarchy of systems, including 2 sets of transformers and an uninterruptible power system, UPS, to get the DC voltages suitable for the chips. Modern AI racks, however, need way more power, like 1 megawatt. Power is equal to voltage times current. Bigger current necessitates having a thicker copper wire. So either we can have a thicker copper wire at lower voltage or a thinner copper wire at higher voltage. At 1 megawatt, with the existing 54-volt rack architecture, you may need up to 200 kilograms of copper bus bars, which is expensive and too heavy considering that this is space that is not generating revenue for the data center. So rather than re-engineering the whole rack and buying ultra-expensive heavy copper wires, we redesigned the whole architecture for 800 volts. NVIDIA says that such an 800-volt DC, or VDC, architecture drastically reduces complexity. With this, the energy internet router type concept of SST might work. Power station builders no longer have to worry so much that their AC or DC power infrastructure will have no customers due to 800 VDC transition issues and get stranded. Not to mention that SSTs take up less space and eliminate a bunch of old hardware. Seems legit enough to me, and NVIDIA does include it into their architecture roadmap. Moreover, wide bandgap semiconductors have gone a long way since the late 2000s and early 2010s. Silicon carbide power semis are cheaper and more capable today, thanks to the EV boom in China, though by no means are they a panacea. Thus, we have a new rush for the SST. There is the aforementioned DG Matrix, which has raised over $60 million for a multi-port SST product that acts like a universal power router to distribute the right power to the right chip. In addition to them, there is Heron Power, which closed a $140 million Series B to bring to market an SST to get around manufacturing constraints in certain larger transformers. Over in Asia, there is the Singapore-based Ampersand, which raised $80 million from Temasek and Walden Catalyst Ventures, which I'm fairly sure is Lip-Butan's firm. And of course, the Taiwanese company that I profiled earlier, Delta Electronics, they recently discussed a future solid-state transformer product which takes medium voltage grid power and turns it into 800-volt distribution voltage for the rack. And in February 2026, they discussed installing an SST inside a data center campus in mainland China run by the company Meituan. And side note, this is basically how this whole video started. I saw a model of an SST in their showroom. I know. The rule goes that when someone leads off their video with a question, the answer is usually no. The transformer is indeed insanely hard to compete against. It has confidently flown all comers to the throne. And of course there are reasons to be skeptical today. Right now, gains are largely from simulations. We have yet to see actual performance data from 800 VDC AI data centers equipped with solid-state transformers. And can it outperform other 800 VDC implementations based around traditional transformers, i.e. hybrid transformers? But there is reason for optimism this time that the SST's time has finally come, at least in some small form. The AI data center build-out differs from the prior hype cycles surrounding the smart grid and train industries. The cost improvements from greater simplicity, removing extraneous rectifiers and uninterruptible power supplies, are significant. There is a real forcing function with regards to this copper problem. And unlike with the smart grid situation, there's a centralized circle of builders and key suppliers who can drive standards or even self-build fast without legacy baggage. So I reckon the door is open. We shall see what comes through. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I will see you guys next time. And check out these sources. I'm still going through them. Have a good one.